Welcome back to Applied Algebra and Trigonometry. We're going to be doing some basic operations with complex numbers. So let's start with the very basic operation of addition. Every complex number has a real part and an imaginary part. Remember, this is always where A and B themselves are elements of the real numbers. And we could take this imaginary number and add another imaginary number to it. Once again, C and D are elements of the reals. And what we would do is add the real parts together. So we would put A plus C together. And then with that, we would have B plus D times J. So although J is a number, J is equal to the square root of -1. When we are working with it in terms of operations with the complex number, we treat it much as we would treat a variable or a unit. Now personally, I find it a little awkward doing this type of addition from left to right. I prefer to write it this way, vertically. And then it becomes clear that you're actually going to add these numbers, and then you're going to add these numbers. So you would again get A plus C plus B plus D times J. It's just a little bit easier for me to imagine it that way. For example, if we add the complex number 3 plus 2J to the complex number 4 plus 4J, we would get 7 plus 6J. We could also add the complex number -1 plus 7J to the complex number -3 minus 2J, and we will follow our rules for addition of signed numbers to get -4 plus 5J. So those were addition problems. We can move on now to subtraction problems. But first we should write the rule for subtraction problems. And the way this works out, actually, is the same way it works out if you distribute the negative to each of those terms and then combine like terms. For example, if we have the complex number 10 plus 2J minus the complex number -5 plus 3J, then we're going to be distributing that negative to both terms in the second complex number. So we will now have 10 plus 2J plus 5, but minus 3J. Now we can combine like terms. 10 plus 5 gives us 15 for the real part, and 2J minus 3J will give us minus 1J. There's our answer. It is a complex number. Let's work through another one, but this time we'll do it vertically. So here's example 4. The example is the complex number 6 minus 5J minus the complex number 12 minus 2J. So even written vertically, we can think of this as distribution of the negative. So this would come in here giving us a -12, and a negative times a negative will give us a positive 2J. And now we can add as usual. So we've taken care of this. We've moved it inside. So we have 6 minus 12. That'll give us -6, and -5 plus 2J will give us minus 3J. So we have addition and subtraction. Let's move on to multiplication. Now when you look at these two complex numbers here ready to be multiplied, it should remind you of the way binomials look when we multiply them, and we are going to handle them in exactly the same way. We are going to multiply A by each term in the second complex number, and then we're going to multiply BJ by each term in the second complex number. So we will get AC, and then A times DJ. Then we will get BC times J, plus BD times J squared. But careful. We know what J squared is. It's equal to -1. So that will make that entire last term change its sign. So we have AC plus ADJ plus BCJ minus BD. And we can combine like terms. In other words, well, these terms, ADJ plus BCJ, they have a common factor there of J. So we can combine those terms. We can also combine AC and negative BD. So that's what happens symbolically. Let's use some numerals in an example. So here's example 5. We're going to multiply these two complex numbers. We're going to do it by distributing this 4. It's going to give us 4 times 2 is 8. And 4 times -5 gives us -20j. We are then going to distribute the 3j to each term in the second complex number. So we have 3j times 2, that's a positive 6j. And we have 3j times -5 for a -15j squared. But we know that j squared is equal to -1. So we actually have here -1 times -15. So this is going to be 8. Let's go ahead and combine these two like terms. Because we have -20j plus 6j, that will give us a -14j, and then -1 times -15 will give us 15. So combining like terms further, we have 23 minus 14j. That is the product of our two original complex numbers. Another example of multiplication would be the square root of -4 times 2 minus 3j. Now, the square root of -4 isn't in the usual form in which we have been writing our complex numbers, so let's get it there. The square root of -4 is the same thing as the square root of -1 times the square root of 4. So we have j times 2, or 2j. So 2j times 2 minus 3j. We will still be distributing here. So that gives us 4j minus 6j squared. J squared, remember, is -1. So we're multiplying our -6 times -1. Therefore, we have 4j plus 6, and written in the proper order, 6 plus 4j is the product. And now we reach the operation of division, and things change a good deal. Division with complex numbers is similar to rationalizing denominators in that we're going to use the conjugate, and that is the conjugate of the denominator, the divisor. So if we are taking this complex number, a plus bj, and we are dividing by c plus dj, we are going to perform that division by multiplying by the conjugate of the denominator. Remember, to express the conjugate of a complex number, always make sure you have it in order with the real number first, followed by the imaginary number. And then you change the sign of the imaginary number, and you have the conjugate. Now at this point, after we have set this up, we have to multiply in the numerator and in the denominator and work it all out. And there you have it. I've distributed properly. Pause the video, confirm that you would get the same thing if you had done this. But now we're going to take a look at these j squareds that we have, knowing that they are equal to -1. And we're also going to notice that we have a positive CDJ minus CDJ, which is going to combine to give us 0. So therefore, we are going to have, let's move this up a little bit, in the numerator, AC minus ADJ plus BCJ, and a negative 1 for the j squared times negative BD will give us a plus BD. And that's all over C squared. There is no j term in the middle, and we have plus D squared. Here's example 7. Now, this might be set up by saying divide 6.5j by 6 minus 8j. You might be given this fraction and be asked to simplify it. There are different ways this could be asked. It does not matter how you are asked. If you have this set up and you want to get to something simpler, you will multiply by the conjugate of the denominator. The real term is the same. The sign of the imaginary part changes. But you use that same imaginary number in the numerator. You use the conjugate in the numerator and the denominator because that means you're just multiplying by 1. You're not changing the value of the original ratio. You are just expressing it differently. All right, and then we have to distribute both in the numerator and in the denominator. All right, that is what we get when we distribute everything. Let's start re-expressing these. We have 48j plus 30j. That will give us 78j. They are positive, so the sum is positive. The j squared in the final term, however, will make that final term negative. And then we have 36. We have a plus 48j and a minus 48j, so we have no j term there. And our j squared will make 64 positive. So now we can continue combining like terms. On the top, we will get negative 4 plus 78j over 100. We are almost done. Almost. Still have a little bit more to do because you must always simplify. Still, let's see, will 4 go into 78? No. So the greatest common factor in all of these terms is actually just 2. So if I factor a 2 out of the top, I will get 39j there. And a 2 out of the bottom, I will have 50. And then these will cancel. And my final answer will be negative 2 plus 39j divided by 50. Now, you may see it this way. Your book will sometimes ask you to go ahead and separate this on occasion, usually when this will reduce to a non-fractional number. And you may also see this written sometimes with the j multiplied there instead of being in the numerator. Both of these forms are equivalent. I am fine for my purposes with the first one, but just be aware that sometimes in the back of the book you may see this instead. All right, one last example of division. All right, let's divide the complex number 2 minus 3j by the purely imaginary number negative 5j. Because we have the imaginary term, we will change the sign of the imaginary term and multiply. Distributing once again, we will get 10j minus 15j squared, and that's going to be a negative 1 there. Okay, on the bottom we have negative 25j squared. Once again, that j squared is going to change the sign in the denominator. So we have 10j plus 15 over a positive 25. Okay, let's get it in the proper order first with our real component and then our imaginary component in the numerator. And it's all divided by 25. Can't stop there. You must reduce when you can. Always do that, though, by factoring out the common factor first. Don't try to just do it in your head or do it without factoring both the numerator and the denominator so you can clearly see what will cancel. And then we will have our final answer. 3 plus 2j over 5. Now, if you technically want to get this into your final answer, into the A plus BJ form, you will have to separate this into two terms. 3/5 plus 2/5 J. As I said, they are equivalent. This to me tells me you know what you're doing. If I want to ask you about actually putting it in this form, I'll make a big deal about putting your answer in that form, and then you just separate this. Okay? All right. I will cover graphing in the next video, so look for it.